Hi there, this is Zhao Suojiang, faculty member in School of Engineering at San Francisco State University. And again, here is part of a series of video help you to better understand the prerequisite for the course ENGR 309, Mechanics of Solids course at San Francisco State University. Today, we're going to talk about shear diagram under point loads. Here is the same simple supported beam that we saw in the previous videos. And in our previous video, we actually calculate what are the reactions at point A at point B. And we have the negative 10 kips, which is meaning it's going downward at point A, and we have the 20 kips pointing upwards at point B. And today we're going to see how we can draw the shear diagram for these particular beams. Before we go forward, one thing to review is the side conventions when we join for the shear diagram, moment diagram, and axial diagrams. And if you cut the beam, take it out and look at the left hand side, and here is the positive direction that you're going to see. The shear is going downward, the axial force pointing outward, and the moment is counterclockwise. And the same beam, if you cut it and take it out from the right hand side, and here is the positive direction for that particular side, and you have the shear going upward, you have your axial force pointing outward, and your moments being clockwise as positive directions. One thing to memorize this is if you put your finger within the beams, your shear is going to be clockwise, creating a clockwise moment to be positive. And same thing for the right hand side. If you're putting your fingers within the beams, if your shear is going to create a clockwise moment, that means is positive. For the axials, it's always pointing outward as positive directions, and for the moments, it's going to make your beam smile is the positive moment. What do I mean by that? Is this: if you have a beam, and if you have a moment, and then your beam is going to be deformed like this, and if you're putting your eyes on it, and that is smiling, so that is your positive moment. Same thing, if this is the beam, you moving clockwise, that is your making your beam smile actions, and that is your positive moment. All right, let's take a look how we can calculate our shear diagrams. First things, we're going to go to a TDOAs. We're going to cut the beam in sections and evaluate what are the shears of that particular sections. And after that, we're going to make an observation to see what we can learn from there. And later on, we don't need to do this tedious process again. First, let's us cut the beams at 1 foot locations. 1 foot, and we have the 10 kips on the point 8. And once we cut it, because we're taking the left portion of the beams, so here is our positive directions. So we're going to have our shears, we're going to have our axial load, and we're going to have our moment. In order to find out what is the shears, what we can do is we can sum the force at y direction going upward as positive directions. Since the beam is in equilibriums, therefore the reaction is going to be zeros. So with that, we can have our 10 kips negative because it's going downward. When we are assuming going upward is positive, minus v, that's equal to 0. And we can find that now v is equal to negative 10 kips. It's negative, meaning that it has a direction is opposite than the assumption we make here. We're making it as downward as positive. If we calculate the answer as negative, meaning our shear is actually going upward. All right, we can do the same thing. Now this time, we're going to cut it at 5.0001 feet. All right, same thing, 10 kips going downward. And we're going to have our 20 kips because we passed that 5 feet point. We're going to have our shear, axial. We're going to have our moment. Same thing, sum the force, at the y direction going upward as positive, what we're going to have is our negative 10 kips plus 20 kips minus v is equal to 0, and our v is equal to positive 10. Is positive, meaning the direction of this force is the same as our assumptions, which is going downward. And we can do this the whole day. Because of the time, I did all the calculation for you. So I'm going to list it as a table. This x is starting from the point A to the right side. And here is our shear. If we're cutting at 1 feet, 2 feet, 3 feet, 4 feet, 4.999, 5.001, 6, 7, 8, 9, 9.999. And here's all the shear you're going to get is negative 10, all the way, negative 10 at 5.001. As we calculate, the shear jump to 10, positive, and it's going to stay that way all the way to 9.999. So if we put those shear force calculated into this diagram here, here's what we're going to see. Start from point 0, you go to negative 10, stay that way for a little bit until the point 5.001, and that become positive 10. Keep positive 10 all the way to 9.999 and become 0 at the end. And here is our shear diagrams. And what we can learn from here, observations. The first point is the shear force changes at external force locations. So if you look at our shear diagrams, whenever we have a force, you can see a jump on the shear diagrams. For example, on the 10 kips going downward, you can see a jump from 0 to negative 10. And at a point where you have a 20 kip force going upward, you can see your shear force jumping from negative 10 to positive 10. The same thing at the 10 kips external force locations. The second point is your shear is going to remain constant when no force between the 2 points. And if you look at our shear diagrams, between point A and point B, we do not have any force in between. Therefore, your shear is become constant all the way. The same thing between point B and your external location. The third observation that we can see in here is your shear starts at end with 0. So at point A, you have 0. At the end, you have 0. If that's not true, a mistake has been made somewhere. You need to try to figure it out. Okay, and that's all for the shear diagram under point load. I'll see you next time.